Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar, Haryana. Today we are going to discuss the module Physics of Semiconductors and Semiconductor Laser from the paper Atomic, Molecular and Laser Spectroscopy. From this module, we'll be able to learn the semiconductor diode, how p-n junction diode can be an emitter, and the semiconductor laser. In semiconductor laser theory, the optical amplification is achieved in a semiconductor material. The choice of material depends on the desired wavelength and properties such as modulation speed. It may be a bulk semiconductor, but more often a quantum heterostructure. For creating the population inversion, pumping may be done by electrically or optically. Light is generated in a semiconductor laser by radiative recombination of electrons and holes. In order to generate laser, different models are assessed wherein many particles interactions are considered that otherwise in simple models are neglected. In free carrier model, carrier plasma is simply seen as a reservoir that relaxes the carrier distribution. Simple models for the gain coefficient are used to obtain a set of rate equations that enable us to dynamically calculate the time-dependent laser response. The semiconductor materials can be broadly classified into two categories, namely direct bandgap materials and indirect bandgap materials. A general picture of the same can be visualized as in the figure. We see a valence band, a conduction band, there is a band gap, energy band gap Eg, and the figure depicts the energy levels E1 and E2, E1 with maximum number of holes and E2 filled with electrons, and x-axis mentions the momentum and the wave vector k, and on the y-axis it is the energy. When electron makes a transition downwards from conduction band to valence band and recombines with hole, a photon is emitted with corresponding energy difference of E2 minus E1, so that HF minus E2 minus E1 is equal to Eg. However, in case of indirect band gap, the lowest energy conduction band electrons have a non-zero momentum. Thus, radiative recombination in this case requires momentum transfer due to photon participation. So, frequency of emitted radiation is given by the equation HF is equal to E2 minus E1, or HFP is approximately equal to Eg. The figure depicts the indirect band gap material where the filled electron conduction band is side apart and the transition takes place from this band. Now coming to the p-n junction, the commonly used semiconductor material for fabricating laser diodes is gallium arsenide, which emits light at a wavelength of 8400 angstrom in the near infrared of optical spectrum. The wavelength of emission can be varied from 6300 angstrom, which is in the visible region, for the third fifth mixed semiconductor gallium arsenide phosphide, to 8.5 micrometer, which is in the infrared region, for the 4/6 semiconductor lead selenide. In intrinsic semiconductor materials, the ambient temperature raises some electrons from valence band into the conduction band by thermal excitation, leaving behind an equal number of holes in the valence band. Photon emission due to the recombination of electron and holes in intrinsic semiconductor is too small. Therefore, to increase the photon emission, we need to increase the charge carrier density by adding dopants. Thus, the energy level diagram modifies accordingly, resulting in an n-type semiconductor material when donor materials having excess electrons are added to it. On the other hand, when acceptor material rich in holes are added to it, a p-type semiconductor material is formed. When these two materials are joined to form a p-n junction, The electrons and holes tend to move in opposite directions across the physical boundary by a diffusion process, setting up a depletion layer sandwiched between the p-type and n-type materials. Across the depletion layer, a barrier potential is set up in such a way that it exhibits further flow of charge carriers, thus establishing equilibrium condition. The electrons and holes which manage to find themselves in the depletion region may recombine with the emission of a photon corresponding to the energy gap Eg. In normal p-n junction in electronic devices, these photons never see the light of day since their numbers are small and efficiency of the production is small in silicon and germanium materials typically used in electronic devices. The figure here again describes the distribution of charge carriers in a p-n junction and the corresponding energy levels, and one can see the barrier potential, energy band gap. So there comes the concept of degenerate semiconductor diode. When heavy doping is done, then the semiconductor material almost acts like a conductor and is referred to as degenerate semiconductor. The figure depicts the p-type and n-type diodes of bandgap semiconductor materials whose energy level diagram is shown here. It very well depicts the active region, change of Fermi level, holes and electrons with p-n junction semiconductor diode with heavy doping known as degenerate. This is without external bias. In ordinary semiconductor junction, electrons and holes will tend to move towards the center under the influence of diffusion and will be balanced by the barrier potential set up across the junction. Charge carriers in this case are expected to recombine in the depletion region and generate photons. This region is now referred as active region. When p-n junction is forward biased, charge carriers are injected into the active region from either side, producing photons as shown in the figure. The generation of photons in the active region is depicted by this figure. When degenerate semiconductor p-n junction is forward biased, holes are injected into active region from n side. So these devices are simple referred as injection laser diodes or ILDs or called laser diodes. In case of non-radiative recombination of charge carriers, energy release is dissipated in the form of lattice vibrations, but in case of radiative recombination, energy released in the form of photon whose frequency is Eg is equal to Hf, or F is replaced by C by lambda, therefore lambda is equal to 1.24 upon Eg. This is the reason that semiconductor lasers became important, because one can tailor the band gap of a material, and by changing the band gap of the material one can get lambda of any interest. Now the point is how to estimate the forward bias voltage to be given to p-n junction. When the degenerate semiconductor diode is forward biased, potential hill is decreased as it is depicted in the figure. Under the influence of external voltage, the Fermi level on the n side is different from that of the p side as it is visualized in the figure, and one can write phi c minus phi v is equal to Ev. The distribution of charge carriers in semiconductor materials obeys Fermi statistics. The probability that a state in the conduction band at energy Ec is occupied by an electron is given by the Fermi function. Fermi function corresponding to conduction band Fc Ec is equal to 1 plus exponential Ec minus phi c upon kT inverse of it, and for the valence band Fv Ev is equal to 1 plus exponential Ev minus phi v upon kT inverse of it. Now the rate at which the photons are generated or absorbed due to transition between conduction band and the valence band is given by corresponding to emission d phi upon dt is equal to C Bcv Fc 1 minus Fv rho of f, and corresponding to absorption d phi upon dt is equal to C Bbc Fv 1 minus Fv rho f. The photon emission rate should exceed the absorption rate, that is, d phi upon dt due to emission is greater than d phi upon dt due to absorption, then and only then we can have the net emitter of photons. Writing their corresponding values, CBCV FC 1 minus FV rho F greater than CBVC FV 1 minus FC rho F. And since BCV and BVC is the same, so writing FC 1 minus FV greater than FV 1 minus FC, therefore one obtains FC greater than FV, and writing the values 1 plus exponential EC minus phi C upon KT inverse of it greater than 1 plus exponential EV minus phi V upon KT inverse of it, we get exponential EV minus phi V upon KT greater than exponential EC minus phi C upon KT. And from the little of the knowledge of the mathematics, phi C minus phi V is greater than EC minus EV, and since EC minus EV is equal to HF, so phi C minus phi V is greater than HF, so one can write EV greater than HF. How to calculate the threshold current density? The photons that are generated in the active region lack direction because of spontaneous emission, and to impart direction to the emitted light and therefore to achieve laser output rather than the just light emission, it is necessary to provide a semiconductor junction in the vicinity of the active region. This can be done by first cleaving the two sides of the crystal, making them parallel to each other to a high degree of accuracy. Then by polishing these two faces of the crystal layer boundary provides a natural reflecting surface. In order to channel the photons along the length of the device, the other faces along the breadth are roughly ground the length of the device. The other faces along the breadth are roughly ground or deliberately edged or roughened to eliminate reflections from these two sides. By further mirroring the back side of the device by coating it with a totally reflecting material, the laser beam can be made to emerge from the front surface of the device as has been shown in the figure. Now this completes the cavity. We have population inversion, we have a semiconductor active material, so the laser system is complete again as those of the similar laser systems. Now because a large number of charge carriers move into the active region when the current flows across the junction due to external bias voltage, the net area of the active region is about 1 millimeter square and its width is 5 to 10 micron. These junction diode lasers are more efficient than the conventional lasers because almost every whole electron pair injected into the active region generates a useful photon. However, part of electrical energy is lost in the form of heat across the electrical resistance internal and external to the diode. But not all generated photons will contribute to the laser radiation emerging from the junction. Now the figure here depicts the emission of laser light from the front surface. Here we can see the partially reflecting surfaces and the device is forward biased. Sawn edges are also seen. These are deliberately made as sawn edges as we want our laser emission in the front surface, or two sides are made totally reflecting surfaces and two are made as rough surfaces. In order to sustain the laser action in the junction, the emitted photon rate must overcome the following losses: the absorption coefficient alpha naught of the device for the photon generated. The second, the losses due to the transmission at the partially reflecting surface at the emitting end of the laser diode. If R is the optical power reflection coefficient of this surface, then the transmission loss per unit length is given by 1 by L log of 1 by R, where L is the active layer length. Third is the diffraction losses in the active region, which are approximately given by an empirical relation given below, and alpha d is written as 0.42 lambda upon n W square. If the total current passing through the active region from positive terminal P side to the negative terminal N side, when forward biased is I, then the current density J is expressed as J is equal to I, which is in amperes, divided by area across which it is flown in square meters. So one can write the current density. As the active region of volume V acts like a resonator cavity, as per the theory of a resonator cavity, it can sustain a number of modes Nf per unit frequency interval per unit volume, neglecting the dispersion. Nf is equal to 8 pi eta cube upon lambda square c. Thus rate of spontaneous emission per mode is alpha is equal to j n eta upon E W delta f nf, j eta upon E W delta f into lambda square c upon 8 pi eta cube, where we have replaced the value of nf. Hence, gain beta per unit length of the active medium is beta is equal to eta alpha upon c is equal to j eta lambda square upon 8 pi E W delta f n square. The point at which the gain in the medium is able to overcome the net loss in the medium is usually referred to as the threshold condition, which is represented in terms of the current density as J threshold. Now, J threshold lambda square upon 8 pi eta E W delta f is equal to alpha naught plus alpha t plus alpha due to diffraction, where we have added all types of losses which we discussed above. The first one was alpha naught corresponding to the absorption coefficient of the device, and the second was losses due to transmission, and the third was the diffraction losses in the active region. So alpha naught plus alpha t plus alpha diffraction. If the two ends of the optical resonator cavity on the either side of the active region have reflection coefficients R1 and R2, then the transmission losses through them is given by the equation alpha t is equal to 1 by L log of 1 by R1 R2, and one can write down J threshold is equal to 8 pi eta E W delta f upon lambda square into alpha naught plus replacing alpha t plus alpha diffraction. If one end is mirrored with 100% reflecting material, although it is not 100%, but ideally taking the value for R1 is equal to 1 and R2 is equal to R, then alpha t is equal to 1 by L log of 1 by R. And since the partially reflecting side of the optical cavity is nothing but the semiconductor air interface, the reflection coefficient can be calculated from the relation R is equal to epsilon r under the root plus 1 divided by epsilon r minus 1, where epsilon r is the ratio of the relative permittivity of the semiconductor material to the permittivity of the free space. Now, in order to understand all the concept, let us go for one assignment, which is to calculate the band gap energy for a gallium arsenide semiconductor material emitting at 0.87 micrometer and computing the minimum voltage that has to be applied across the junction in order to create a condition for net emission of photons from it. For a semiconductor device, we can write down Eg is equal to h nu is equal to 6.6 into 10 to the power minus 34 joule second. This is the value for h, and nu c upon lambda. C is the velocity of light and written as 3 into 10 to the power 8 meter per second, and lambda we have been given 0.87 micrometer. So writing 0.87 into 10 to the power minus 6 meter, the value comes out to be 2.28 into 10 to the power minus 20 joule. And for the junction to act like a net emitter of photons, V has to be greater than equal to h nu upon E, which is equal to 2.28 into 10 to the power minus 20, the value which we have calculated above, divided by E electronic charge is 1.6 into 10 to the power minus 19 coulomb, and the answer comes out to be 0.142 electron volt. So this much of the voltage we need to apply to create or the net emission of photons from the given material of gallium arsenide. So let us summarize what we have learned in this model is the semiconductor lasers, and nowadays semiconductor lasers are getting popular in comparison to the other lasers. As with the advancement in material science, we are able to tailor the band gap of the material, and hence we can get the wavelength of our choice. As we understand, the wavelength lambda is equal to Hc upon Eg. By changing Eg, we can get the changed wavelength, and by choice of the material we can get a laser of our choice. In this module, we have understood direct and indirect band gap semiconductor, PN junction, energy level diagram for N-type and P-type semiconductor material, distribution of charge carrier in PN junction semiconductor diode with heavy doping known as the degenerate semiconductor diode, generation of photons in active region, that how optical amplification is possible in semiconductor and how light is emitted from PN junction. We have also discussed estimation of forward bias voltage and threshold current density. Thank you.